Hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So, I am your tutor for the physics subjects. So, we will continue the discussions on electric field due to a charged disc in this class. So, we got the results, the Ez sigma over 2 epsilon naught 1 minus z by z square plus r square, right. So, for z greater than 0, and sigma over 2 epsilon naught minus 1 minus z divided by square root of z square plus r square for z less than 0, right. And we plot this as a functions of z in the previous class. So, now today we will consider some limiting case where the case 1 so where we consider the distance z is very greater than r. So, again the distance z, just quickly draw a diagram. So, this one is charged disc and the distance, the point P we consider there, and the distance is z. So, this point P above the plane or maybe below of the plane, that depends on the sign of the z, vector, sign of the z vector. So, this one is x axis, y axis, and this one is z cap, x cap, y cap, and this is the origin. So, in the case z is very greater than r, so we first expand this by using the Taylor series expansion. So, use Taylor series expansion. So, 1 minus z square root of z square plus r square 1 minus 1 plus r square by z square by minus half, right. So, basically we take this z as a in the denominator 1 over z square and into the square root and then simplify this. So, now we expand this in the power series expansion. So, 1 minus half r square over z square, so only consider the leading order term. So, these are the higher order terms. So, this 1 cancel, the remaining part is that half r square by z square. So, this is the leading term. So, then the electric field Ez becomes, so therefore, the electric field Ez sigma over 2 epsilon naught r square by 2 z square. So, it can be written as sigma pi r square over 4 pi epsilon naught times z square. So, now we calculate the total charge of the disc. So, the total charge of the disc Q. So, sigma is uniform. So, basically the surface integral sigma times ds, the integrate over s. So, sigma, since the sigma is uniform in this case, it is taken out of the integral sigma, and what is the ds? The area of the surface area of the disc. So, this is 2 pi, is pi r, right, the surface area. So, this is basically sigma pi r. So, we plug into this, pi r square, So, this is sigma pi r square, right. So, this is the area, so sigma times pi r square. So, now if we plug into this expressions Ez, equations 1, so we get Ez becomes 1 over 4 pi epsilon naught q over z square. So, this is exactly the electric field due to a point charge with a charge q. So, that is expected. So, this is electric field due to a point charge, electric field due to a point charge q, right. So, this one is expected. Okay. So, when we are looking the point at a far away from the disc, so the disc becomes a point charge, okay. Means all the charges are concentrated at a point with the total charge q, and that is the idealization of a point charge, okay, that we discussed in the previous class. So, this one is expected. Now, another case 2, the other limit where r, the radius of the disc, is very greater than z, okay. So, this limit basically implies that the infinitely plane, so infinite plane, okay, and you consider the electric field extremely close to the surface of the plane. So, this is basically implies that the plane. So, now the disc, and if the radius of the disc is very large, so it becomes a plane, okay. So, the plane is very large, okay, and the field points, or other way we can say the field points, okay, P is extremely close to the surface of the plane. Close to the surface of the plane, okay. So, we consider a disc, the radius is r, okay. So, one thing, if you consider a point P here, okay, and the radius of the disc is very large compared to the distance z, right. So, that means you consider an infinite plane, okay, or in other way you can say that this point is very close to the disc, okay. So, such that if you are looking for the disc from this point, it is again infinitely large, okay. So, you can reach in the two way this condition, okay, and the electric field in this limit. So, therefore, the electric field in this limit, so E, so we use the vector notation, so E vector becomes sigma over 2 epsilon naught k cap. So, k cap means that the z cap, okay. So, the unit vector in the z direction, this one is denoted by k cap, and this is I cap, and this one is j cap, okay. So, this k cap for z greater than 0 and minus sigma over 2 epsilon naught k cap z less than 0. So, basically the direction is opposite, okay. So, magnitude is sigma over 2 epsilon naught above the plane, and the below the plane is same, but the direction is different. So, in the above the plane the electric field pointing upwards, that means in the z directions, and below the plane the electric field becomes downwards and the minus z directions, okay. So, minus k cap direction. So, in this limit if you plot this, so the electric field is constant, it does not depends on the distance, okay. When the distance very close to the disc, for z greater than 0 is constant, for z less than 0 gives a minus sigma over 2 epsilon naught, okay, and this is plus sigma over 2 epsilon naught, and that there is a discontinuity, again the finite discontinuity, okay. So, finite discontinuity remains there, okay, because the finite discontinuity comes from the point above the disc and the point below the disc, okay. So, there is a difference. So, this difference is remains there, okay. So, if you calculate the discontinuity of the electric field when you cross the plane, okay. So, you notice that note, so discontinuity in electric field as we cross the plane, okay. So, that means the plane of the disc, okay, plane of the charged disc, and the discontinuity is given by okay. So, the discontinuity is given by delta Ez. So, this is the amount of discontinuity, E z plus, that means above the plane, and E z minus, that is the below the plane. Okay. This is sigma over 2 epsilon naught minus sigma over 2 epsilon naught. So, total is sigma over epsilon naught. So, that is the discontinuity, okay, the amount of discontinuity. So, that the conclude is that so given a surface charge density sigma, okay, so the normal component of the electric field, so given a surface charge density sigma, okay, sigma on the surface, so then the normal component of the electric field, normal component of the electric field always exhibits a discontinuity, electric field, okay, across the surface, across that surface always exhibits a discontinuity. Okay, with the amount of discontinuity delta E n is sigma over epsilon naught. So, here n denoted as the normal component, that means the z component, okay. So, the perpendicular to the plane. So, if we calculate the x component, y component of the electric field, okay, at above of the disc, okay, and this becomes 0, right, and we calculate the below point. So, this become continuous, okay. So, there is a no discontinuity in the parallel, okay. So, only perpendicular component of the electric field has a finite discontinuity, okay. So, okay, so that is all about the surface charge density. So, next we will go into the next charge distributions, okay. So, the next one is the volume charge density. So, volume charge density. So, the volume charge density, the same way we define. So, this is the generalizations of a surface charge density, okay. So, if we consider a small volume, okay, within the V, so let us say consider a small cube, okay, and the volume of this small cube is delta V I, right. So, ith cube, okay, and the charge is delta Q I, okay, and you calculate the electric field at this point P, okay, the direction is, so this one is r cap, okay. So, basically the whole volume, okay, is a sum of small element, okay, small cubes, okay, because now the volume is a 3D object, okay. So, the charge density, the volume charge density rho r, okay, as a functions of r, the distance from the center. So, this becomes limiting case of del V I tends to 0 and delta Q I over delta V I, right. So, this is the general way we can define the charge density, okay. So, we first consider a small strip, okay, for a linear case, okay, and for a 2D problem we define a small element, okay, surface element, okay, for 3D problem we define a small cube, okay, and then is a limiting case. So, that means is the size of this small object tends to 0, okay. So, we define a continuous variable. So, this is dq over dv, okay. So, now the dq and dv both are continuous variable, okay, a limiting case. So, then the charge density So, this is the rho r. What is the dimension? So, in this case the dimension of rho r, charge per unit volume. So, coulomb per meter cube, right, the unit is coulomb per meter cube. Okay, this one is the unit, okay, SI unit. So, and the total charge, now it is easy to calculate the total charge. So, total charge q h integral over dq rho r dV. Okay. So, the concept of charge density is analogous to the mass density. Okay. So, if you know that, once you know the mass density and how to calculate the mass, is the same way that the m rho m r dV, right, and integrate over the volume V. So, this one is a mass density and this one is a total mass, right. So, similarly the total charge q just rho v rho r dV, right. So, let us do a quick example. So, suppose rho r k r, okay. So, vary with distance, okay, linearly with the distance r, right. So, then the calculate q becomes k r and dV is 4 pi r square dr, right. So, then k times 4 pi r to the power 4 over 4, right. So, we consider a sphere of radius r, so 0 to r, right. So, k times 4 pi r to the power 4 over 4. So, this one is pi k r to the power 4, this is the total charge. Okay. If we consider a sphere of radius r and the charge distributions varies linearly with r, okay, we calculate the total charge in this. So, in the next class we will discuss the Gauss law, okay, and some of the applications of Gauss law, okay, and how to solve a problem using Gauss law, okay, quickly. Okay. So, we will see in the next class. Thank you.